Mingalapa. Kinmiha. Kyonaami, Myoman man, Kapate. Akulachi, Kudi Kate Unabe. De Gontakito, De Du Beta Thanamarta One Tan Sao Ne Pate. May I talk you, my presentation in English? So, I present the lesson on Chem 4108, Chem 4208. Physical Chemistry 6-4. As continued episode 1 previously. Here we go. I presented the symbols used in mathematical expressions and their SI units before. So, as revision, you should revise the symbols, the names, and their SI units given in the box. It is wrong at all the given things at the right you see. Do you remember the SI unit of cell constant as well? Try it out. Okay. You have good memory. So, shall we compute a problem? The molar conductivity of 0.05 molarity solution of MgCl2 is 0.01942 per ohm, square meter, per mole at 25 degrees Celsius. A cell with electrode that are 1.50 square centimeter in surface area and 0.50 centimeter apart is filled with 0.05 molarity MgCl2 solution. How much current will flow when the potential difference between the two electrodes is 5.0 volt? Here, you must notice that it is given 3 portions in the problem for the same MgCl2 solution. Firstly, molarity C and lambda molar C are given to us. So, specific conductance, kappa can be calculated from these given parameters. I think you do so. You are given area and length in the second part. But, units of both must be converted into SI units. Okay. Using the values of kappa, A and length, you can compute the resistance R. So, R equals 34.33 ohm. After that, you can calculate the electric current, I, from equation of I equals V by R. Right. You finally will obtain that I equals 0.1456 ampere. Let's move to limiting molar conductivity. It is called as lambda molar infinite. It also may be defined as the sum of ionic molar conductivities of cations and ions, each multiplied with the numbers of ions present in the formula of the electrolyte. Here, you notice something else. It is impossible to determine the values of limiting molar conductivity for weak electrolytes at infinite dilution. That is, you can measure it indirectly from the limiting molar ionic conductivities for the individual ions of a weak electrolyte. If you study a problem of exercise number 4, then you will become more understanding this case. The problem is that the limiting molar conductances of NH4Cl, NaCl, and NaOH in aqueous solution at 25 degrees Celsius are 0.01497, 0.012645, and 0.02478 per ohm, square meter, per mole, respectively. Calculate the limiting molar conductance of NH4OH. In problem, it is given the values of lambda molar infinite of NH4Cl, NaOH and NaCl respectively. In finding the value of lambda molar infinite of NH4OH, as described the previous slide, this must be calculated indirectly. How you calculate the value of lambda molar infinite of NH4OH? You must rewrite as described in equations 1, 2, and 3. You follow as so, and anionic lambda molar of chloride ions are cancelled. And, similarly, cationic lambda more of sodium ions can be cancelled. The rest are cationic lambda molar of ammonium ion and anionic lambda molar of hydroxide ion. When it has summed, lambda molar infinite of NH4OH would be obtained. As so, when 0.01265 has subtracted from the sum of 0.01497 and 0.02478. it will be finally obtained that lambda molar infinite of NH4OH equals 0.027105 per ohm, square meter per mole. Next, shall you try exercise number 5? It is as similar as exercise number 4. The limiting molar conductance of NaOH is 0.02478 per ohm, square meter, per mole. Calculate the limiting molar conductance of completely ionized water at infinite dilution in the solvent water at 25 degrees Celsius. Here, lambda molar infinite values of NaCl and HCl are 0.012645 and 0.042616 per ohm, square meter, per mole respectively. In exercise, it needs to calculate the lambda molar infinite of H2O. Are you okay? Try it out yourself. Continuously. I talk about degree of dissociation of electrolytes, alpha. The degree of dissociation of an electrolyte is the ratio of the molar conductivity of a solution at a given concentration to that of the solution at infinite dilution. As expression, alpha equals lambda molar C divided by lambda molar infinite. So, degree of dissociation, alpha, has no unit. Here, shall we go one derivation? I present the derivation of alpha and Van 't Hoff factor, I. So, assume that an electrolyte AB with molality M has become dissociated partially to form cation of Nu plus, Azat plus, and anion of Nu negative, Bzat minus, for this given chemical reaction. In the reaction, electrolyte AB is equilibrium into Nu plus Azat plus Nu minus Bzat minus. At initial, the electrolyte AB is 1. Since it does not dissociate into its ions, then A, Zat plus, and B, Zat minus, have 0 only. When it becomes dissociation, let alpha be the amount of ions, A, Zat plus, and B Zat minus, become dissociated from electrolyte AB. At equilibrium state, the electrolyte AB has become reduced, 1 minus alpha, and positive ion, A, Zat plus, and negative ion, B, Zat minus, have become Nu plus alpha and Nu minus alpha, respectively. For molality M, it had become M, 1 minus alpha, for electrolyte AB. M, Nu plus alpha, for positive ion. And, M, Nu minus alpha, for negative ion, respectively. As total, M, 1 minus alpha, plus Nu plus alpha M plus Nu minus alpha M. Since there is a common factor, alpha M, at the second term and third term, on the right hand side. So, equals, M, 1 minus alpha, plus Nu plus Nu minus into alpha M. Again, since Nu plus Nu minus equals Nu, total equals M, 1 minus alpha, plus Nu, into alpha M. Then, Van 't Hoff factor, I, is that I equals M, 1 minus alpha, plus Nu alpha M, divided by M. So, I equals M into 1 minus alpha, plus Nu alpha, divided by M. Here, M has cancelled. So, I equals 1 minus alpha, plus Nu alpha. Then, rearrange that. I minus 1 equals Nu alpha, minus alpha. Then, alpha is a common factor on the right hand side. So, I minus 1 equals alpha into Nu minus 1. Finally, we rearrange that. Alpha equals I minus 1 divided by Nu minus 1. Since alpha equals lambda molar C by lambda molar infinite. Therefore, we had got the relation that alpha equals lambda molar C by lambda molar infinite also equals I minus 1 divided by Nu minus 1. Shall we do exercise number 4? The problem is described that The dissociation of sulfuric acid would now be described in terms of the complete first-step dissociation of the strong acid H2SO4 to give H+ and HSO4- ions, followed by the partial dissociation of the weak acid HSO4- ion. Use this idea and estimate the degree of dissociation of the hydrogen sulfate ion. M equals 0.01 mole per kilogram, I equals 2.46. Here, we do notice that sulfuric acid is a strong electrolyte. So, first, it completely dissociate into H+ ion and HSO4- ion. And HSO4- ion is a weak acid. Then, HSO4- ion partially dissociates into hydrogen cation plus sulfate anion. Here, let 1 be initial amount of HSO4- ion. H plus B0 and SO4 minus B0. At state of equilibrium, it becomes dissociated equal amount of alpha in H plus and SO4, 2 minus ions. So, HSO4 minus becomes reduced to 1, minus alpha. For M molality, HSO4 minus becomes M into 1, minus alpha. And, H plus and SO4 2 minus ions become the same amount of M alpha. As total equals M plus, M into, 1 minus, alpha plus, M alpha plus, M alpha. Then, M plus, M minus, M alpha, plus 2M alpha, equals 2M plus M alpha. So, total equals M into, 2 plus alpha. After that, we consider Van 't Hoff factor, I equals M into, 2 plus alpha, divided by M. Here, I value is substituted by 2.46 on left side. On right side, M is cancelled. So, 2.46 equals 2 plus alpha. Finally, alpha equals 2.46 minus 2. Alpha equals 0.46. Okay. Let me stop here. Finally, I advise you. You learn something every day. Thank for your time. I will be back. See you later.